So here's another old AP exam question. This one's from the 1999 AB exam, and it's problem number 4. It's a no calculator question, and we'll try to do the first several pieces of this in this video. And they give us a situation where we have a function f. It's got a continuous second derivative for all x's, which basically just means the second derivative is always defined. If the second derivative is always defined, that would mean the first derivative is always defined, and if the first derivative is always defined, that means the function is always defined. So we don't have to worry about the function or any of its first two derivatives being undefined in any locations. Now, they do give us some values of the function. Well, one value of the function, f of 0 equals 2, a value of the function's derivative, f prime of 0 is negative 3, and a value of the function's second derivative, the second derivative at 0 equals 0. And then they talk about this second function, g, and the derivative of g is given by this, and g depends on f, and its derivative depends on f prime. So we're going to need this a little bit later on. We don't need it in part A. Part A should be pretty easy. It says write an equation of the tangent line to the graph of f at the point where x is 0. So to do this, we're going to need to know the slope of our tangent line evaluated at x equals 0. So to find the slope of our tangent line evaluated at the x value of 0, that's going to correspond to f prime evaluated at 0. And f prime evaluated at 0, they've provided for us. They've told us that f prime of 0 is negative 3. So there's no work at all in finding what f prime of 0 is. We just steal it right from the problem statement. So here's the slope of our tangent line. We also need to know a point on the line. Well, the point on the line is going to be the x-coordinate of the point of tangency, comma, whatever the corresponding y-coordinate is. So here's the point of tangency, but they tell us what f of 0 is. They tell us that f of 0 is 2. So the point of tangency is 0, comma 2. All we have to do now is write the equation of a line that has this slope, goes through this point. I'm going to use point slope form, so y minus y1 equals m, which is negative 3, times the quantity x minus x1. So there's point slope form for the equation of the tangent line. If you wanted to write it in slope intercept, as always, that's your choice. But here is a form for the equation of the tangent line. In part B, they want us to decide whether or not we can determine if f has an inflection point at x equals 0. So think about what we do when we find inflection points. An inflection point occurs anywhere where we have a change in concavity. So what we find is we find the second derivative. And we set the second derivative equal to 0. We set the second we try to figure out when the second derivative is undefined. Well, they've already told us the x value we're supposed to be concerned with. We're supposed to be concerned with the x value of 0. They tell us what the second derivative is evaluated at 0. F double prime of x equals 0 at the x value of 0. So basically what this means is if we were trying to build a sign chart for the second derivative, now there might be some other values where the second derivative is 0, or there aren't any values where the second derivative is undefined, right? They tell us the second derivative is continuous, meaning it's defined everywhere. So there might be some values where the second derivative is equal to 0, but what we would have to do to fill in this sign chart for the second derivative is we would have to have the capability of determining what the sign of the second derivative is to the left of 0 at an x value like negative 1. And if you go back up to what you're given, you don't really have that capability. You also don't have the capability of figuring out what the sign of the second derivative is over here. Now, if the second derivative sign chart ends up looking like this, positive to the left of 0, negative to the right of 0, that would mean our function is concave up to the left, concave down immediately to the right, and we would have an inflection point at 0. But based on what we know, there's absolutely positively no way for us to determine if the sign chart looks like I just had it, or if the sign of the second derivative is actually positive on each side of 0. So because we don't know a way, because we can't find a way to determine the sign of the second derivative to the left of 0 and to the right of 0, we're not going to be able to conclude with whether or not we have an inflection point at 0. It's possible, but we can't be for sure. So is there sufficient evidence? Nope. And I'm not going to really write out the explanation. We just kind of talked it through over the last minute or so. You should also be able to fit part C in here. So part C is the first piece of this problem that has you working with this new function, g of x. And they want us to take this fact about g. G of 0 is 4. and we want to write an equation of the tangent line to the graph of g at the point where x is 0. So just like we did in part A for the function f, we're going to need to know the slope of the tangent line to g evaluated at x equals 0, and that's going to correspond to g prime of 0. So what is g prime of 0? Well, they were nice enough to provide us with g prime of x right here. If we want to know g prime of 0, we're just going to have to put 0 in place of all the x's in g prime of x. So I put a 0 in that exponent, and then I have a quantity. We're looking at 3 times f of 0 in place of the x there, and then plus 2 times f prime, and a 0 in place of that x as well. And now it's just a matter of evaluating this. Well, negative 2 times 0 is 0. E to the 0 is 1. Anything to the 0 power is 1. So we have 1 outside the parentheses. They told us, and we used it earlier, what f of 0 is. F of 0 is equal to 2, right? So I can put 2 right in place of f of 0. So if I do that, and then also put negative 3 in place of f prime of 0, we actually have a pretty simple expression to evaluate here. We're looking at 1 times the quantity, 3 times 2, and then plus negative 6. And if you evaluate inside the parentheses, you're obviously looking at 0. 1 times 0 is 0. So you end up with a slope of 0 for your tangent line. So now you have to figure out what the point of tangency is. Point of tangency is going to have an x value of 0 and a y value. Since we're tangent to g, the y value is going to be whatever g of 0 equals. Well, they told us that. G of 0 equals 4. So our point of tangency is going to be 0, 4. So to finish things off, write the equation of a line that has a slope of 0 and goes through the point 0, 4. If you want to do this in point slope form, it's going to look a little bit goofy because typically we don't use point slope form when our slope's 0, but since that's what we did in part A, we'll go ahead and we'll do that initially here as well. But what we typically are going to do when we have a slope of 0, this side of the equation is essentially 0. If we solve it for y, we're going to end up with y equals 4. So that's going to be a horizontal line that goes through the point 0, 4. And that is it for part C. I have to do a second video here to wrap things up for this problem and take care of part D.